So it's a bit of a mixed bag this session. So first we are hearing from Maxim, which is a recorded message. So he's like a ghost here. And then he can't at the same time talk from the, so I hope that he's on Zoom. He can't at the same time talk from the computer and from Zoom. So then after this is finished, we'll switch over to Zoom. And hopefully he'll be able to answer questions. And after that, we will discuss whatever was heard in this section.
Guys for not being able to come. Let me just briefly highlight a few points that I think are important. First, from the observed properties of the repeater FRB and known distance, we can estimate the radiation energy density and then the equipartition magnetic field, and the real magnetic field can be larger. And that equipartition magnetic field evaluates to about 10 to the 8 Gauss. Also, we should require that the radiation energy density is less than energy density of emitting particles. So then we can express the conditions on the internal properties, Lorentz factor and density, in terms of the observed brightness temperatures. And we can also take into account bulk Lorentz factor and anisotropy. And generally these conditions can be satisfied both in rotation and magnetically driven paradigms. Okay. An important point, from the given observed properties of the radiation, we can estimate this laser intensity parameter A, and that estimates to about almost 1 million. And in case of in vacuum, this would be the momentum in terms of MC of the transverse momentum of a particle, and that is a huge value, and that will lead to huge radiative inverse Compton and synchrotron losses, so that a loss time can be shorter than an pulse duration, and that's a problem. And the resolution is that if you have external magnetic field sufficiently high, so that the cyclotron frequency is larger than the observed frequency in the plasma frame, then instead of high oscillations with momentum of the order of A, there is just a drift, relativistic drift with a Lorentz factor basically of unity. So large magnetic fields are required to avoid catastrophic normal losses. Next point, from the observed properties of the repeater, the requirements of high power and constant properties exclude rotationally power pulsars as FRB sources. Magnetically driven are still okay by energy. For example, you can imagine some kind of initial stage of a reconnection flare. There are some weak observational limits that perhaps can constraining now. One of the most interesting events of the last year was observation of the frequency drift in 2 repeaters, both high to low frequency drift, and that reminds of solar type 3 radio bursts, and that indicates there is some kind of a stiff confining structure, most likely a magnetic field, and then you can develop radius to frequency mapping models. This could have been also due to constructive interference through a changing lens, but then you would expect these drifts up and down, but here we have 2 that are both down. And now actually these drifts were kind of predicted for the predicted radio emission from magnetars, and even before the discovery I was saying that one may expect the frequency drift of the peak of radio emission characteristic of type 3 bursts. And again, you can construct models of radius to frequency mapping, basically assuming that within a magnetosphere at a given location the given frequency is emitted, and then you can typically will have linear frequency drifts, and also the rates that you expect do match the observed ones. And then there is a prediction that sometimes the drifts would be more complicated, and then there is a clear prediction that there should be polarization angle swings through the burst. just like in pulses in the rotating vector model. But in case of FRBs, if the emission comes from the closed field lines, those polarization swings will be smaller than in pulsars. Thank you.
Okay. Can we switch over to Zoom now and see if Maxim is there to answer questions? Maxim, are you here with us?
Can you hear me?
Are you? Is it you, Maxim? Okay.
Can you hear me?
We can hear you a little bit. Are there any questions? Can you hear us, actually?
Yeah, very well.
Okay. Are there any questions to Maxim or comments? Andrei.
What is the punchline?
Can you use a microphone, please? So we can hear you?
Andrei Gruzinov was asking, what is the punchline?
The punchline is the required magnetic fields are very high at the location of FRB. The field should be at least 10 to the 9 Gauss. That's a very good thing for magnetospheres of Newton stars. The second punchline is that narrow frequency bands are kind of expected in the plasma laser model where local plasma properties determine the dispersion properties. And finally, the drift observed in FRB. First, all down. So I did this presentation a couple of weeks ago when there were only two known. Now there is more than a dozen known FRBs. All of them show downward drift. And that tells me that there is a kind of stiff confining structure that controls the frequency. And the most obvious case is magnetic field. So emitting like the propagating magnetic field produces somewhat different frequencies. So it propagates probably outward, so the field's decreasing. And also the rate of the drift. They measure this drift rate over almost an order of magnitude. The rate of the drift also consistent with somewhat under the 8 centimeters, so using some magnetosphere. So I see this very different arguments all pointing towards the magnetospheric origin. That doesn't say what is the emission mechanism. It's not much general than any particular emission mechanism, the argument that I just made. Yes.
So where do you think the people who do synchrotron masers, what is the mistake that they're making, in your opinion?
I don't think they make a mistake. It's just the observation of narrow frequency bands that reaching frequency. This is much better fit with, I would say, distance confining structure. So we have now 1,000 and maybe 2,000 cases where we see frequency, narrow frequency drifting down. This is a new observation over the last half a year, and I think that it's much better fit for the magnetosphere of neutron stars. And then we can imagine actually two mechanisms. One is rotationally powered and one is magnetically powered. And rotationally powered probably doesn't work. Rotationally powered like the giant power system trap. Because the power that we need for the first repeaters when we get a concept, the powers are just way too large. They will be larger than any expected spin down power. The magnifier model has its problems because if you produce this intended horizontal in radio, you would be much likely to produce 1055 an optical and 1050 an X-ray. But that cannot be true because 1050 an X-ray is having the generator, and we know that the rates are wrong. So in case of magnetite, there should be a mechanism that produces very quiet radio bursts without putting much energy into optical electrons, and it is challenging.
Okay.
Yeah.
We can only hear, well, maybe 50% because of the noise. The connection is very noisy. So I don't know if we are there any comments from? Ah, it's bad here. It's bad here. I don't have the right measure to deduce.
We need to invest in a microphone.
So Maxim, it's sounded it's very interesting, but your comments are not yet clearly heard by the audience. I don't know if you can if you send me an email or something like this, I can flash it later on in the discussion because the connection is not great. So okay, at this time, I think we should make a transition to a discussion, right? Unless there are some comments about.
We have a question from the Zoom chat. It's on the screen right now.
Okay. Well, I don't want to answer this question. Okay, I think we should make a transition to a discussion. So perhaps I can ask members of the panel to come to the front. And one thing is that I have asked Harish to share something with us. I was hoping he would share something to do with sun, but he had like more philosophical. Is this all? You are part of the panel too. And Vikram is not. Vikram is not here. Roger, do you want to come to the front? Yuri Lubarsky. Why don't you come to the front? Yes. So this is the wisdom from Harish, Gruzinov's hero. Maybe.
Come on. Okay. Yeah, so this is more to set up the discussion. I put this together very quickly, so it's probably not polished. I just want to kind of highlight some of the interesting propagation effects. So this is only related to propagation, not necessarily engines or emission mechanisms. And just want to make like a general comment that it like doing some propagation effects feels a little bit like there and back again. We kind of rediscover some of the things which were known before, but we just see it in a different light, because once you know that there are FRBs, you're not the same person again. And so, yeah, so it's something to keep in mind that a lot of these things are there in literature, and it's just applying it to in a new regime. And so I just want to highlight what are some of the new things we can do, which we couldn't do before FRBs. So I'm just going to move from the largest scales to your right to the smallest scales towards us. And again, this is just to set things up for the discussion. I don't have any results particularly to show. So on a gigaparsec scale, I think there are kind of two interesting things I can think of. One is related to scattering. What's interesting about a gigaparsec scale is that the distance arm is so large that you only need a small angular deflection to make an enormous effect in scattering, right? So it's kind of allows us to look at the small scale structure of the circumgalactic medium and perhaps the IGM in a way we could not do that before. And there's a lot of interest in that in the CGM in particular right now, because it's kind of related to a lot of UV spectroscopy. So our initial thinking was that the CGM is, is at the virial temperature. So for the Milky Way, it's 10 to the 6 Kelvin, and you can't cool that within a Hubble time. But observationally, we know that there's a lot of neutral gas through almost every CGM sight line. And so the question is, what kind of cooling instability gives you that gas? Or how is that gas sustained? And so we are really talking about small scale structure in the CGM. And scattering is the best tool we know to probe sub-parsec scale structure at these distances. So it's kind of interesting that FRBs came around the same time, and so we could say something about CGM structure and what cooling instabilities are operating there. The other thing I can think of is strong lensing. And so this has to do with the amount of, let's say, cosmic matter in strong lenses. Anything of a fraction of an arc second to above has been probed already very well. So we have tight limits there. And anything of a stellar mass of order or below is known very well from microlensing in the galaxy. So I think the interesting thing there is that intermediate mass regimes, so like something like 10 to the 3 solar masses to maybe 10 to the 4, 10 to the 5 solar masses, where there's no easy way to probe it. But having an FRB gives you a very nice way to probe that mass range just from the time delays in a lens. So I think that's something where FRBs are kind of unique, and it's something which is not easy to achieve with other means. So coming closer, on a kiloparsec scale, it's the ISM of the host galaxy itself. And so I think we could do all the interesting things we did in our galaxy with pulsars in other galaxies. But I don't see anything like fundamentally different there other than what is the ISM in different types of galaxies and getting that from propagation effects. So the same things as in the Milky Way, asking the question, are other galaxies ISMs different? So it's a little bit of marginal progress, I would say, in that. So once you come to a parsec scale, at least in some models, you're getting close to the FRB, and at least in 121102, there's a persistent source. So there's some reason to believe that there might be transrelativistic plasma in this regime, either because it's shock-heated gas or what have you. And so once you have reasonably dense, at reasonably high magnetic field, so I'm talking of tens of milligauss magnetic field, and once the plasma is transrelativistic, then Faraday rotation, you have to go to the generalization of Faraday rotation, which is conversion of all three Stokes Q, U, and V to one another. And so that can be a really nice probe of this, the central parsec around the source, where in some models at least, there's a good reason to believe the plasma is transrelativistic. I must also say that related to what Andrei spoke about, you don't need a transrelativistic plasma. You could also have a very high magnetic field. And in regions where the field is exactly perpendicular to the sight line, you could get some conversion to Stokes V. So that's a nice way to get at the field structure, radial field structure, which you couldn't do in many other cases. So that's something on.
But the frequency dependence is different, right? The frequency dependence for conversion and this reversal is different from conversion and in this transrelativistic regimes. This is correct, right?
I think both of them are lambda square. What is different is that in having a quasi-transverse region, you get what you're really measuring, what you're calling conversion measure, is the Faraday rotation of the Faraday rotation up until the quasi-transverse region. Because in the quasi-transverse region, you're coupling the modes. So you're mixing left and right hand. And so you're actually really measuring the Faraday rotation up until there. Right? So that's lambda square. And even in a relativistic gas, that rotation is lambda square. But the amplitude is not lambda square. The magnitude of the effect is higher. But it goes as lambda cube roughly. Yeah. And so once you get much closer to the source within an AU, we heard some talks about it, and some of the things which we couldn't probably do without FRBs is what happens when you're in the strong wave regime. So basically, the way I always think about this, which probably is helpful, is we all studied Thomson scattering, and so you have an electromagnetic field, the electron oscillates, and then it scatters radiation. We always forget the V by C cross B term there, because V by C is much less than 1. But now if the electric field is strong enough, then you can't forget that. So there's also a Lorentz force on the particle. And so you don't get simple oscillations in one plane. And so that leads to nonlinear effects where the effect depends on the strength of the wave itself. right? And so you can have dispersion that is dependent on the strength of the pulse. You can have Faraday rotation dependent on the strength of the pulse. And so that's a nice way to probe the, something like the central AU from the source. Yeah.
Because this is exactly. Thank you. This is, if I understand correctly, is exactly the paper which Sturl Finney and
Yeah,
his
yeah, yeah,
young
yeah,
collaborator
yeah,
wrote.
yeah.
And when the, sorry for this young collaborator, when he presented this thing, it was very interesting, right? So they were having dispersion and rotation measure, which were dependent on the amplitude of the wave.
Yeah.
And I thought that it is unmeasurably small. But yesterday, maybe we can ask Sturl to clarify this thing, but yesterday Sturl said that we can in fact measure the differences in the dispersion measure, which are as small as 0.001 parsec times centimeter minus 3. And when I asked, for example, Laura, she said that this is not something like that everybody knows. This is apparently some new thing. So what I would like to, maybe you can explain to us, what is the current status of this high precision measurement of the dispersion measure?
Ryan should present it, since it's my former student, his former student here, and who did it.
This interruption.
Yeah, please, yeah. I mean, I'm not moderating anything. Yuri is the moderator. So I was asked to present a slide, which I did. Yeah. Ryan, you want to say something?
So what we can do is we can look at these very narrow pulses, and we've got a series of 4 of them. 2 of them are relatively strong. The pulse widths are on the orders of a few hundred microseconds for the 2 brightest ones, and we're able to measure the precisions on the order of like 10 to the minus 3 DM units. The 4th pulse, which is a bit fainter, looks like it's got a dispersion measure that is different to the first 3, and the difference in the apparent dispersion measures on the order of 10, sort of 4 times 10 to the minus 2 DM units.
Were you able?
Yeah.
Were you able to establish that indeed delta dm scales as the amplitude, as intensity of the wave, as predicted by the theorists?
You're talking about 2 different things, right? You're talking about deviation from power law minus 2.
Yeah.
I'm talking just
the actual DM. The full.
I am asking. I thought that theorists wrote a paper claiming that higher amplitude pulses are more or less, I don't remember the sign, more or less dispersed than low amplitude.
Yeah.
Since you are measuring on latitude accuracy, my question is very simple. Have we established the correctness of Finney and his collaborator result?
It's the opposite sign.
Let me
No, the sign was the opposite.
No, the sign is correct.
Yeah.
The sign is correct. The dimmer one has a higher DM.
That's correct. Then
the sign is correct. But it turns out, I mean, you can call it fortunately or unfortunately, that the 2 brighter ones, which should have the strongest modulation, they have the same DM. It's just the dimmest one, the dimmer one, which is different. So it does not fit in the if you strictly apply, it does not fit the luminosity dependence or the amplitude dependence of DM.
Wait. The amplitude could be. So these are subpulses. So you're saying the 2 bright ones, they don't have the right.
The 2 bright ones, their amplitude differ by a factor of 10. But we didn't see DM difference. But for a dimmer one, which is even dimmer, we see a DM of difference. So
are you sure that it's not profile evolution?
Yeah. That's what I wanted to ask. So Ryan?
Yeah, I was gonna. If I can plug in and show you. That might be the best
thing.
thing.
Yes.
So if you just give me a second, I'll kind of get things prepared.
Roger.
While he's getting ready, could I just ask, with this defined dispersion measure correction, is it possible to make new statements about the intrinsic widths of subbursts? And I was listening to Jim, of course, this morning, and contrasting with his feeling that
But Roger, why is it related to the dispersion measure? Or sorry, why is it? It's not related to the strong wave regime or any of that, right? That still follows the pure dispersion law. Right. Yeah, while he sets up, I guess my point was the lambda square sweep is still the lambda square sweep to first order if you change the electron mass, right? Because of a strong wave. So you would apply it as if the dm was some other value. Yeah.
No, but I guess the point is that
Oh, I see what you're saying. You're saying why don't you de-disperse different parts of the burst? Okay, I get the point. Okay. Yeah, yeah. Yeah. Got it. Yeah.
Subpulse, subburst structure is, because I think that's really rather diagnostic.
Okay, so here's the four components. So you get the big stick. Yeah, so you can just see these are the four pulses here. This is of course the Fourier frequency averaged pulse profile. Here's now what they look like in Stokes components. So I guess, I mean, one thing to keep in mind is also they have different polarization properties as well. The fourth one is, I mean, it's very apparent in Stokes V. So it's almost, I mean, as much as you can say for such a weak component, it's, you know, 100% circularly polarized. So think about that. And here's what the profiles look like. I mean, you know, this is one of these plots you have to go and print it off on a piece of paper and look right down the edge of it. If you guys remember doing that, that technique here. But the point here is that this fourth one here, it doesn't show up. I've been working with Hiran to try to get sort of the plots to best convey this, but it definitely has a different sweep here.
So Ryan, I guess the question is that one trombone unit of?
Well, yeah. Well, we can measure it. It's point one. It's 0.1. Yeah. It's got the right. It's got higher. Yeah, which is what.
DM is higher for lower luminosity burst.
it could be a higher DM, but like as Jim says, it could also just be two pulses like this, right? That are
exactly. Yeah, it's got the same sense that that repeaters have. And there's a couple of other of the bursts.
Ryan, could you go back? Do you need a bigger telescope?
Yeah, pulse 2 is the faintest one.
So, Roger, I think it boils down to how do you want to interpret those, as a DM or as a trombone unit that's intrinsic or for whatever reason. And I'd say we don't know.
I think just to clarify, I think the calculation that Wayne did is correct. The question of whether what the density surrounding the material is, whether this explains that is a totally just to comment again, like, so if you look, for instance, at the McKeely paper, there's one burst that's 30 microseconds wide. You use that to determine the dispersion measure. You apply that to all the other bursts. Some of them are nicely straight. A few of them, though, show a weird kind of sweep still, and it's hard to tell whether that means they have a different dispersion measure or you're not resolving the structure in the burst.
Yeah, I agree. I call it apparent dispersion measure, not dispersion measure.
You haven't finished, right? You're done the show.
Going to be true of any dispersion. I mean, you have to have. You're constraining a certain, let's say, fraction, if you will.
Yeah, it's a small fraction of the DM contribution within, actually at a distance much less than a parsec. Maybe 10 to the 16, 10 to the 17 centimeters. Yeah.
I think we should say that the free is much more diagnostic, in my opinion, than the DM effect. So that we discussed the effect of the free.
So you want to see the spectrum then?
Yeah.
Is there any evidence for free? I mean,
Okay.
that's very, very interesting. But is there any evidence for free absorption
Can,
in this?
so,
Can you use your seat mic, please?
how about while I'm up here, I have the floor. I don't know if this result is related or not, but this is observations of, it might be related to what Roger just said, of a galactic magnetar 1810 taken with a broadband system at Parkes. And this is just what the pulse profile looks like at a certain epoch. The red here is showing you the total linear polarization, and the blue is the circular polarization. And what you're seeing here is, again, what the RM looks like if you measure it at different rotational phases. I'll call this a parent RM. And these are now showing you the sort of, I guess this is the linear polarization position angle, and this is the other angle, which tells you what the angle of circular polarization is. This is work being done by a PhD student at Swinburne. This is now showing you basically what the spectrum of the FRB looks like. Oh, sorry, of the magnetar, excuse me, looks like at different pulse phases here. And the important thing here is that you end up being gigahertz peaked right in the middle, where you've got all this circular polarization. So now we'll just take slices through the spectra of the magnetar at these different pulse phases. And I guess this one's a bit ratty, but as you go towards the middle of the profile where you get the circular polarization, you can see how you're seeing the propagation effects here, where you're having something's happening which is causing the linear to sort of convert into circular polarization. So
how many pulses are averaged here? This is average pulse.
This is averaged over, probably a 10-minute observation.
Yeah.
So, but I mean, the interesting thing is that, where you're getting all this circular polarization, you are getting this sort of, exponential cutoff spectrum. So, again, this is sort of, I mean, maybe it's a word of caution about interpreting frequency average pulse profiles, or the opportunities to look across a pulse frequency to try to disentangle what's going on here.
Yeah. So what we know from pulsars, especially when you average many pulses, is, I mean, we see in individual pulses we see these 90-degree jumps.
Yeah.
In linear in the polarization angle, and sometimes coincident with that is a flip in the circular polarization.
Yeah.
And then when you average a bunch of pulses together, some of that transition stuff gets blurred.
Yeah.
And it's also a little bit frequency dependent. So I'm wondering if something like that is going on here. It's really still all intrinsic to the pulsar, but it's this flipping.
Yeah, exactly. And I guess, some of the questions would be for these sort of, I guess I call them magnetospheric propagation effects or relativistic propagation effects. What are the frequency dependencies that we would expect to see, and how can we test them?
So if I can just go back to the nonlinear stuff, I don't know if Bing you want to comment, because in terms of the amplitude, I was reading your paper. There's also a focusing effect, because in the center of the pulse, basically the electrons are heavier, so that means that it's a higher refractive index than outside the pulse. So you also focus, and that influences the amplitude. If that is a nonlinear effect, then what Weibing was saying can be rescued, right? The two pulses not agreeing with each other. You want to say something about that?
Could you use a microphone?
Can you use your seat mic, please?
So Yuanpei looked into some laser physics. So that is well known in the laser, very strong wave regime. So what he did is basically looking into the laser physics and look up for the analogy with FRB. It looks like a lot of effects can be just transported to FRB. So the squeezing effect, it is there, but it depends on parameters. If the density is high enough, then there could be a beaming effect. FRBs can be even narrower. That will affect the, say, collimation angle, will affect the number density, the event rate density. Probably there are a lot more that not beaming towards us if that regime really reached. But it's parameter dependent, so please take a look at that paper. So it's unfortunate UMK is not here, and every time he's a very shy guy, and every time he's not invited, so hopefully he can be more exposed. He has a lot of very nice papers in the future.
Okay. Well, unless we want to look at slides, I suggest that the panel sits in front again. And I was wondering if the panel members have any other points that they want to make about propagation effects, polarization. Any of you have some thoughts?
Not
Jim?
a point. I have a mic. It's not a point. It's a question that goes back to what I asked in the talk about whether the synchrotron maser in the shock or one of the shocks can amplify incident radiation. And it seems on general principles it could, because you can analyze it with Einstein A and B coefficients. So if you get spontaneous emission, you should also get absorption or negative absorption. So I'd be interested in knowing.
I actually had a
ins
question
and outs of that
around the talk. So which I didn't ask, so now is a good time. The growth rates for some of the masers which were presented yesterday were like 10 to the 4, 10 to the 5, something like that. So in a millisecond, you can easily reach 20 or 100 e-foldings. So why do you need an incident radiation? You can just take a completely weak field and then grow it to...
Well, no, I'm saying suppose there is incident radiation, then what happens to it? I mean, let's look at it this way. There's only one persistent source known. One wonders if there are plenty of FRBs that have no circumsource stuff around it. So that means you have to have the central engine make the burst. Now, maybe that's too extreme of a case, but
I guess that distinction is important if the number of e-foldings you can get before the maser saturates is insufficient to grow the waves from the thermal background level, and you need a much bigger seed initially.
I think the issue Yuri can comment as well, but I think the issue with the shocks is that the behind the shocks is this really hot plasma, which is very good at scattering waves. And so if you have a central source that's trying to come out through that, even if it was sort of transparent, it kind of gets scattered by that relativistic plasma. So that's kind of why we favor the FRB coming from the forward shock as opposed to the reverse shock, because the reverse shock emission we have to go through this shocked material. Maybe Yuri can comment on that.
The point is that this region, the reverse population, is very narrow. It's about 1 Larmor radius. The growth rate of this instability, in fact, smaller than Larmor period. Not much, but smaller. Therefore, the problem is that optical depth across this maser is smaller than unity. And therefore, in this case, there is no significant amplification. What is possible, because this is shock, why we see this instability. For example, this wave could be amplified. I suspect that what we see is either scattering of this wave, or all this quantum language is a bit cheating in this case, because in reality, these are classical systems.
Sure.
Okay. In this case, what is this instability? We have a ring, and due to this instability, inhomogeneities are formed at the ring, and they rotate and radiate. Therefore, for example, a wave propagating in this direction produces these bunches rotating But these bunches rotate and they radiate it in all directions. This is not amplification in the same direction. But this is okay. The classical language. In this case, I think that initial radiation is of no importance.
Unless it is important. In other words, if the central engine is producing bursts, radio bursts, then there may not be the situation around every FRB source that you get a synchrotron maser. I guess is what I'm wondering.
If you believe it's synchrotron maser,
yeah,
it works at the site of the shock.
Sure. No, I understand that, but I guess I'm just saying across a population of burst sources, you may not have the conditions to get a synchrotron maser, so you have to explain the burst some other way.
Right. There are other mechanisms. I try to present another mechanism which is not related to synchrotron maser. But for a while, there are not so many different mechanisms.
Andrei Viloborodov, I saw your hand.
You already explained how, but basically, I think Jim's question was how
Can you push on the mic?
I did.
Oh, okay.
Yeah. Jim's question was whether you can amplify a seed wave, but the outcome of this amplification does not depend on the seed anyway. That's one point. It amplifies whatever it can amplify at the right frequency. And the other point is that it's not easy to eliminate the maser because it's moving with speed of light and it's localized, like you explained. So if you have something that it's a layer which moves with almost speed of light and it's very tiny. So it's all internal business of this layer. Whatever comes out from this layer, just classical bunches that develop by themselves and they emit whatever they can emit. It's not even easy to interact with some other source. Because they are causally disconnected normally.
I want to bring the discussion from the emission mechanisms, which we already had a session on, to actually propagation mechanism. In particular, I want to ask maybe the panel members or the audience members, what are the prospects of constraining magneto-ionic environment of repeating fast radio bursts from polarization measurements? Is there any new data which is going to become available? Any new theoretical work that people think should be done? It's a question to everybody.
The obvious thing is you discussed earlier whether we can measure linear polarization, circular polarization across a range of frequencies, right? Laura spoke, maybe she could say something more. That's sort of one question is whether you could, what are the prospects for testing this conversion process that you propose?
Right. So
I'm switching. I don't know what the question. I mean, I guess maybe you could have some back and forth about what the quantitative magnitude of the effect is, and whether it could be measured.
The short answer is for repeaters, it's significantly easier. For one-offs, it's harder, but you get enough of them.
Can I ask a question about how we would actually find that Stokes V spectrum that Andre showed? So the oscillations were like a kilohertz, right?
Yeah, these are really fast oscillations.
Yeah.
Related to the fact that you are rotating very fast over
there. So you need baseband data at a low enough frequency that you actually have Faraday conversion. You then need to up-channelize the data such that you have a huge number of frequency channels, probably to the width of the pulse. And then I guess you FFT in the frequency direction. Is this the algorithm? That could be done.
Yeah, you would derotate Stokes V the same way you would derotate the linear hands.
Well, except there you just have a single Faraday depth, and like if you have three.
Well, let me backtrack. So there are two ways you can get Stokes V starting off with linear polarization. Okay, one way is what is called quasi-transverse propagation, which is what Andrei spoke about. You have a magnetic field almost at 90 degrees, and it should.
Sorry, Harish. I thought the question was when and is it even feasible that the observers will actually measure it? No.
Yeah, but the answer depends on which conversion is happening. That's why I want to explain that. So in that way, what's happening is at that quasi-transverse region, you're taking some energy from LHCP, putting it in RHCP, taking some from RHCP, putting it in LHCP. So it's a coupling between the modes. They're not independent in that region. So no geometric optics in that region. And so what happens is whatever normal Faraday, vanilla Faraday rotation has happened before you hit that region, the Stokesby has an imprint of that because of this coupling. And so again, you'll have more Faraday rotation, and again, some coupling might happen. That's why there were distinct peaks. Each peak tells you that you have crossed one of these coupling regions. So you would derotate Stokesby exactly the same way you would derotate Q and U. And then you would try to find peaks. Each peak would correspond to, and then the difference would, one of these regions, difference would correspond to the total Faraday rotation.
And just to amplify what Harish is saying, this is the way to find it. It may be that you wouldn't see it in another way unless you do this type of derotation or Fourier transform or whatever.
Otherwise, it's just depolarized.
So for that, you would need to you would need to have the channel width, which you would need to derotate Q and U anyways. Okay, so in that paradigm, the other way you can get Stokes V is if.
Can I interfere? Yeah. But can they even measure this V at 1 gigahertz over the bandwidth of 1 megahertz? Is it even feasible?
Yeah. Like Jason said, there was baseband dump in the EVN data, and we tried that. It's feasible. Yeah. It's doable.
So Andre, in your example, you had something like a 50 kilohertz frequency scale.
Right.
Yeah, but that's if I understood it, it's related to the delta R.
Thickness of the.
But okay, so what determines delta R? I mean, what kind of range of delta R's? Yeah. Okay.
Yeah,
so we should look for a bunch of different frequency scales.
Right.
Then.
This is what okay, like I said, it would be ridiculous for me to tell people what to measure.
But no, it's an important point that it informs the search strategies, right? If it oscillates rapidly, if you don't know this, you wouldn't see it.
But I don't understand one simple thing. Isn't it what observers routinely do? Look in their actually recorded signal for patterns which have never been seen before or something. Like I don't know.
You're not going to see the oscillation by eye. You're not going to see the oscillation by eye. You need to derotate.
You need to take a Fourier transform with respect to lambda squared, right? If you do that, then you would see something. But if you don't do it, you wouldn't see the signature.
You're saying it is a non-trivial statement that it should be Fourier.
I'm not sure. That's why we have a discussion, right?
I mean, it's also the data is very noisy, right? In most of the cases, it's not clean enough to just say, oh, this is a pattern and this is good enough.
It's signal to noise starved.
You have to get it with some match filter to be able to get it out of the noise. Anyway, just finishing up. The other way you can get conversion is you don't have any of this transverse field. You don't need any of that. All you need is the plasma to be relativistic, which is doing the Faraday rotation. So once the plasma becomes relativistic, the modes are elliptical in general. And so you can convert to V. And in that case, you're in general, because relativistic plasma doesn't interact with wave, very strongly, like non-relativistic, you will convert to V, but you probably won't get this 10 to the 5 rotation measure from a relativistic plasma. So in that case, that 10 to the 5 in FRB 121102 comes from some other plasma, which is in the line of sight, and you could still rotate some of this to V, and if that rotation happens before the vanilla Faraday rotation, then you don't have to derotate V at that fine resolution.
Can I talk about rotation measure? Where does it actually come from? What do people think? Which part of this? I mean, I'm talking about 121102 specifically. Which part of 121102 do people think rotation measure comes from?
Possibly the nebula, right? Because it's been seen to decrease if the nebula is expanding.
But the nebula is very hot, right? The nebula has relativistic electrons, just like Harish was saying.
Yeah, that's part of the point, is that the nebula has relativistic electrons to explain the persistent source. But then Harish is right that you need separate populations. You need a relativistic population to explain persistent radio emission, and you need a non-relativistic population to explain.
So my question to you is it possible that these two populations coexist in the same region of space, or do you actually need to have a separate screen for non-relativistic populations?
I think both options are viable, but I mean, yeah.
But from the point of view of plasma physics, is it really feasible to have non-relativistic, significant amount of non-relativistic electrons embedded in the same location?
I mean, we see filaments. which are non-relativistic.
Okay, so it has to be spatially separated.
Yeah, you form clumps and.
I mean, the galactic center magnetar has a RM of 60,000, and Sag J star has an RM that's an order of magnitude larger than that. Right.
Well, let me just make the point that if it's a nebula that's expanding, there was an earlier time where there were a lot of electrons injected that have had time to cool. So, if you think there can't coexist a cold population of electrons on a relativistically hot one, then that would be a problem. But I think there are reasons to suspect if it actually is a nebula that there would be a sizable cold population, because the cooling time is, when things, a few times less compact than at current size would be very short.
Bing, you wanted to say something?
My 2 cents. The first thing is the only place we know that has such huge RM is near our supermassive black hole. So one straightforward explanation is that this source is near a black hole. Within the magnetar scenario, as Brian and Ben have been advocating, I have been discussing with Ben, not directly to Brian yet, but I like to ask this question because if you want to produce FRBs, your B field is actually in the plane, which really, to our observer, is essentially B perp instead of B parallel. So you need a very ordered B perp to produce FRBs. And then somehow you further down, you convert this huge B perp to a huge B parallel, and it's a net B parallel because if you just randomize this B perp to B parallel, it's still you don't get a very large RM. Somehow you
exactly the same question.
Yeah.
We are talking. Sorry for interrupting.
Yeah.
I think it's very much related.
Yeah.
To
Okay.
what you're saying.
Go ahead.
There is this on Monday, Ravi was smiling and saying there is nothing to talk about. This FRB 121102 is almost certainly, just by chance, happens to lie close to the center of the galaxy. The observed changes in rotation measure are almost certainly proper motion. We have just to forget about it and not interpret this nebula is as Ben and Ellie and Brian are doing as a circumburst thing, but just an. Do I understand what you are saying correctly? It is just an accident, and we are pursuing an empty goal.
No, but I think Bing is actually making a more specific point that can be answered by people who think about this magnet nebula. The point, if I understand correctly, is that to get rotation measure, you need the field along the line of sight, and to get polarization, you need a coherent field,
but
which
still
is.
The conclusion is that this is nothing intrinsic to the magnetar. It's just an accident. And indeed, we have seen from your slide that all these things have much smaller rotation measure. It's just some outlier. There is no nebula there. We are misinterpreting everything.
Could be. It could be, of course, that this is the interpretation. I just want to make the comment that this hot radio-emitting plasma has to be confined by some colder plasma. Otherwise, it would just run away. And we know what the parameters should be. And as we discussed, this colder plasma, which is shock heated by the hot, high pressure, persistent radio emission plasma, just it would maybe a coincidence or maybe something. The thickness of the shock heated higher density confining plasma, which is at much lower temperature. The electrons there are not relativistic, unlike the persistent plasma emitting the radio waves. They could provide just the right rotation measure.
Why in this source only and nowhere else?
Again, because for the same reason that it has only this. This is the only one that has a persistent emission.
But this persistent emission is the supermassive black hole.
No, it could be that it's just. It could be. You may be right, but it could also be that it is a young source compared to the others.
Yeah.
Well, let me also make there's a distinction. If you look at the magnetic field in the Crab Nebula past the termination shock, it's not a purely toroidal field anymore. There's all types of instabilities which take a purely toroidal field and make it a mess. And so we don't. Maybe people actually have a quantitative measure of what that is, but there's a distinction in these models we've been developing where the shocks are going through a region of free definitely toroidally wrapped in an ordered way versus what happens in the nebula where there are kink instabilities and other things that have time to.
So in a sense, you're saying the same thing as Ellie, or almost the same thing.
Yeah, I think Ellie wants maybe is saying that the RM could happen in our language the supernova ejecta shell, and we still think it's possible the RM could come from the nebula from cold electrons that have had time to cool since its early evolution. So it's actually slightly different. He's saying the RM could come from the supernova ejecta. I'd say we don't know what the magnetic field would be of a supernova ejecta if it would be high enough.
No, but
But
that's
I think
also addressing
one
Bing's
statement
point.
that can be made is that if the relativistic electrons in the nebula, which give you the synchrotron emission, and they are now cooling either because of synchrotron losses or adiabatic expansion, if that electron population marches all the way down to gamma equal to 1, it will violate the Faraday conversion limit. It will violate that.
Sorry, in
cannot
what?
do it this way. But
The one way to not have enough Faraday conversion is to keep all the electrons highly relativistic.
Can you explain, Ellie, why you say you cannot do it? Do you have a more expanded thought?
No, but because of what Harish is saying.
Yeah.
You're saying Faraday conversion is an issue.
Yeah, not
Yeah,
seeing
so
Faraday
there's
conversion.
a sweet spot in parameter space. For certain parameters, you're absolutely right, but there is a
so
sweet
I'm
spot
saying
where
that sweet
you can
spot
get a.
is either have the entire nebula ultra relativistic, like gamma 10 or higher,
No,
something like that.
So I don't think quantitatively that's true. I think qualitatively you're right that there's these two things pulling in opposite directions, but I think you can find a parameter space where they still fit the data.
But I think this is sort of, to my taste, it's a bit too much tailoring things. If you just take the simplest thing, take a hot plasma and confining plasma, and you derive the parameters, the dispersion measure increase of like 1 parsec per cubic centimeter per year, and the rotation measure are consistent with this thin shock heated confining plasma parameters. It could be real, it could not be real, but it sort of, you don't have any more free parameters. It just fits.
But if it's a shell, its field should be continually diluting by flux. I don't understand how the magnetic field would stay so strong.
The magnetic field is just the magnetic field also is not a free parameter. To get the rotation measure, you need to assume that it's close to the equipartition of the shock heated plasma. So if you know the density, yes, you know the velocity. If you assume it's close to equipartition, you get the right numbers. Could be this, could be just a coincidence, but this is just. It's an it's an electron. Yes, it's just an electron proton plasma that you shock. You don't have any problems with the conversion. So it could all be just a coincidence, but it could be says something.
Well, we've heard there are other FRBs that have excess RM over what we would expect just going through the host. So it can't be. I mean, I can give you one. I use terminology, Vicky. I can give you one tooth fairy. If you want to start saying that a very large number of these just happen to be near supermassive black holes that otherwise have no connection to the supermassive black hole, then that gets worrisome for me.
Yeah, so I wanted to get to that too. So if you look at the other FRBs and then let's apply the same thing we did to the other ones, there's Faraday rotation and some of them have Stokes V. And given that their rotation measure is not ludicrous, I think the only way to, if Stokes V is not intrinsic and if it's happening in let's say, mildly relativistic or non-relativistic plasma, the only way to do that would be to have the conversion to Stokes V closer to the source where the plasma is trans-relativistic, so gamma of few or 10. And so that way Stokes V is not rotating in those cases, Ryan showed us. Right? Stokes V, he didn't have to derotate Stokes V at all. He only had to derotate Q and U. So there's some amount of conversion that's happened in trans-relativistic plasma close to the source, and that extra Faraday rotation is just coming, that's vanilla. It's just cold plasma away from the source doing it. I think that's what would fit it, but I'm not so sure that there's nothing intrinsic to the source which is giving that Stokes V. So I just wanted to ask, is this commonly seen in pulsars, like what Ryan showed?
Bing?
And another piece of information, exactly the same point, we actually looked into the RM in our galaxy for both pulsars and magnetars. And magnetars as a function of B field, as a function of age. There's essentially no evolution, and the only higher RMs are the ones closer to the black hole. Even for pulsars, when you get closer and closer, there's a slight trend that RM goes up. And for all the others, magnetars and pulsars with different ages, they're all like several hundred-ish. That might be an indication. You can still argue that, okay, the magnetars for 121102 is too young, maybe so special, but we don't see some transition from like 10 to the 6 suddenly to 100.
Ask, because I'm staring at this paper by Opperman et al., the galactic Faraday sky from 10 to the 4 extragalactic radio source or something. They have a map. And looking at it, roughly a third of the galactic plane within about 5 degrees of the galactic plane has RMs between 300 and 500, which are the maximum that are seen total in any of these. So I don't understand the argument that there's evidence that the host can't possibly produce an extra RM of 200 or 300. I mean, a third of the galactic plane seems to be doing it.
A third of the galactic plane, but
it's looking along the plane.
No, but the question is where the sources are, right? So it's true that it's looking up from from our position, which is not in a dense star-forming region where maybe FRBs are made. But if you were looking up out of a dense star-forming region, it looks to me like your typical RM is going to be several hundred, at least in the Milky Way.
Yeah, I think I agree with that.
So I mean, it's not that you necessarily need something within 10 to the 16 centimeters. I mean, it could be 50 parsecs away.
I think it's only for 121102 that you need that.
No. But the question that was being raised, there were many. Brian was saying there are many of the FRBs require excesses of 100 or 200, and I'm not sure that I see that needs a special local source.
My question was: is the Stokes be typical in pulsars? What we see?
Another question I have for the observers is: do the other repeaters that CHIME has seen, or anyone, I should know this, have they shown any time variability? Because if you saw time variability in RM, right, then that would tell you it's from the galaxy, right? So I guess that's my question: is to the other.
Well, it's for CHIME is not that easy because you have a ionosphere. For CHIME is not so easy because you have the ionosphere. So if the RM is low, it's difficult to detect variations of 1 RM unit, and we don't have the capability of detect extreme rotation measures yet. So
This is the obvious way to go forward to test this, right? Is to look for time variability. I'm not saying you're able to do it yet, but
we're moving in that direction, absolutely.
I guess that's not specific to CHIME. The ionospheric RM is of the order 1 unit. It doesn't matter which frequency or instrument you measure it with. That limits your.
Yeah, sure.
So does I don't know too much about RM, but so the FRBs which are being localized to the outskirts of ellipticals, do we actually expect to see any? I mean, are there cases where there has been a high host RM for those FRBs? No.
No, we agree on no over here. Okay, that's good to know.
I was wondering if we should take this discussion from, unless there is more on polarization, if people have more thoughts on polarization. I think this is
I want to comment on Bin's question. So it's actually not difficult to make a perpendicular magnetic field a little bit tilted towards you if you just invoke some ellipticity. The supernova remnant is not spherical, so you get some cosine theta. Can get to 30 degrees, can get to any degree. So even a toroidal field can have parallel component, right? Can get you some RM.
Yeah, but when you produce FRBs, the B field needs to be original in the.
Yeah, for that, maybe Lorenzo, you wanna.
Andrei Belobrodov.
In case for magnetars, you have to produce FRBs much closer in the region which is much smaller compared to the region where you hope to have rotation measure, tip for basic models, I think. And so it's like Brian mentioned already, you have toroidal field in the outflow. If it's made this scenario for magnetospheric model, also it's kind of different story. But the nebula itself well, it has some preferred direction for the flux, but there's no reason to believe it's a regular field, and it's in the Crab Nebula. It's not probably regular. It's basically destroyed and turn around and do have parallel component.
Lorenzo.
Quantitative note on that. So the paper by Porth that did 3D simulations of the MHD simulations of the Crab Nebula, purely toroidal field in the wind. So this is where we would put the FRB generation. You have amount of energy in the radial component in the nebula, say by eye averaged over the azimuthal component that is over a point few. So 0.2 strength in the magnetic field in the radial direction as compared to the toroidal field in the nebula. So I think that should be. And the fluctuation is of order on the nebula on the nebula size. So I think there will be line of sights where you get this component.
I just want to quickly ask Ryan. So I'm still trying to figure out if there's anything worth pursuing here, or it's just not useful in terms of at least the circular polarization. So the profiles you showed me, or you showed us, is that when you saw that they were like, oh yeah, it's like pulsars, they do this all the time, in which case it's probably related to emission physics and at least, yeah. Okay, so there's nothing strange in the Stokes V profiles you see. 100%, for example. Some do. Okay. So it could be related to just the intrinsic emission.
Yeah, which again, but pulsars emissions producing magnetospheres.
Right. Yeah. By intrinsic, I mean it is within the magnetosphere, not in some nebula that need. So we don't need to put in any nebula there to explain any of this.
Harish, what's your preference?
Whatever the truth is, I don't care. I really don't care. But that's good to know. So this could all be a red herring. It's possible that it's a red herring.
But it's also true that the ASCAP FRB that looks most like the repeater, a repeater is 100% linearly polarized with a flat polarization position angle. So, I mean,
it's a class of objects.
Yeah, they're different. Yeah, there's two. We've got a handful that look like the one that Hiran has worked on. So it's kind of.
So likely red herring to do all of this, but maybe not exactly 100%.
Well, I guess, yeah, pulsars can produce circular polarization in pulsar magnetospheres. So if you're going to produce FRB emission outside of a magnetosphere, it also has to be able to produce circular polarization.
Is it understood when pulsars make purely linear polarization, when they make a mixture? Is the emission mechanism understood for pulsars? But from a polarization point of view.
Well, in principle, pulsars to get 100% polarization is not a big problem. Just to produce one pulsar.
I think Sasha has a
Can you please use your microphone?
Definitely, most of polarization phenomena are due to propagation, even in pulsars. But of course, 100% polarization couldn't be produced by propagation. Therefore, it is intrinsic. But it is quite possible.
Sasha?
Euro just said everything I wanted to say. I mean, if you produce near the star in a strong field, there is no way to produce circular polarization. All the normal modes are 100% linearly polarized. So polar cap radio emission has to be 100% linearly polarized unless it propagates through the magnetosphere. You get something like a Faraday conversion and get something like 10% circular polarized. So this was papers by Yura and Petrova back in end of 90s. So the giant pulses are sometimes highly circularly polarized, but they're produced in a different region. They're probably produced near the light cylinder where the modes are no longer 100% linearly polarized. So I completely agree that 10% is, at least in pulsars, 10% is a propagation effect. 100% circular has to be an emission process.
But Jim said that some of them, 100% circularly polarized. Isn't
I don't think those are like polar cap radio emissions, right?
Well, yeah, I would agree with that. It has to be some kind of conversion process, but it can make close to 100%. And then the Crab giant, the shot pulses, even within 100 microseconds, some of the shot pulses flip sign of circular.
Okay, are there any other comments about polarization, both observers and theorists?
So what is creating such rapid variability, and would we expect it to be generic to all AGN? My recollection is that it's something like a few massive stars in the galactic center that are making winds, and if you're in the right regions, you pick up.
Yeah, when those winds collide, in principle, there is quite compact structures, compact dense structures that can intervene along the propagation. I'm just, I'm waving my hands.
All I'm saying is it's not so obvious that something orbiting a supermassive black hole can create rapid variability in these quantities. That's my.
But
it does happen to this magnetite.
It does. It's empirically.
Yeah.
I mean, I would say something of the environment rather than the
It's
magnetite
the
itself.
I'm just saying.
Right?
Yeah, I'm just saying I don't understand.
Brian is saying it's not an orbital period. This is like this is the first order natural time scale. But there are other things that happen, just like you said yourself.
I read recently a few papers by Quattert and Elliot Quattert and many others, Stone. They are modeling accretion onto the galactic center from windy stars, and they see, of course, lots of turbulent, highly magnetized things. And so I was wondering, your point is well appreciated, but if I just take their numerical simulation and put whatever, 1,000 kilometers per second peculiar velocity, whatever you call orbital velocity, maybe I will get this fast. Maybe it's not obvious to me that 1,000 kilometers or whatever is not enough, given highly turbulent nature of their accretion.
Well, I have to say, okay, this magnetizer is not so close to the black hole. It's 0.1 parsec away from the black hole. So it's not sitting where Stone and Quattert and others.
Still, the environment is very dirty.
So the environment, that's exactly right. The environment, just like Brian said, it's close to the region where there is a lot of massive stars. These massive stars drive massive winds. The winds collide. Collisions are clumpy. You have a lot of warm, dense clumps of temperatures of like 10 to the 4 Kelvin. So it's still enough, hot enough to produce wonderful plasma effects. I wanted to talk about scattering because I think we have like 20 minutes left, right, or something like this. And I wanted to ask Jim, first of all, two questions. One question on Jim and others. First of all, what do you think are these screens that are giving scintillation arcs and galactic pulsars?
Oh, the thin when you have the thin
screens.
I don't know, shocks of some kind, but there have to be quite a few of them.
But there is always one along the line of sight to any pulsar, right? Maybe sometimes two.
What, one of these arc things?
Mm-hmm.
Yeah, but some no, I don't think that's quite true. I mean, some of the local ones have several, and when I say local, I mean within a few hundred parsecs. And so for those lines of sight, it looks like they're just a series of very discrete things. Other lines of sight looks like it's a more continuous scattering medium, and then the arc is thickened, and it fills in. Because basically you're just superposing a bunch of thin things. So it's a mixed bag as to what we see.
So is there any prospect of finding out what these things are, whether they're associated with some actual object or whether they're just like a fluke of interstellar turbulence?
They don't have much column density of DM. You don't need very much. So that's one thing. I don't know. it's a tough call. I mean, who knows? Maybe the Voyager spacecraft will go across one of these.
So we've been using Meerkat to observe 0437,
yes.
And Daniel Reardon processed that data, and he actually sees 8 scintillation arcs between here and the nearest pulsar. And one of them has such a low rate of curvature that it's consistent with being in the bow shock, which is about, I think, 8,000 AU or something from the pulsar. So that one's associated with the shock.
Wow, that's amazing. Andre?
I was naively thinking that this screen of yours is something which gives rise to phase delays, right?
Yeah, yeah. It's just a phase-changing screen. Yeah, yeah.
But if you have a shock, it's not a column density. It's just a jump from n equals 1 to n equals 4.
But if it's got...
Would it be a good screen? Because it
No,
shock by itself does not produce...
No, you have to have fluctuations transverse to the line of sight.
So it would be a shock which is kind of a
That's
line...
corrugated or something.
Corrugated and aligned actually.
Yeah,
like this.
yeah. You got to have fine-scale structure. But it seems to be thin along the line of sight, to get these arcs. But I just do want to emphasize, we don't, thin arcs aren't the only things that are seen. Some of them are much thicker.
Roger?
Yeah.
Refractive part of it. So, although there's not a lot of column density there, there is a lot of turbulence, and we know that because they've got.
Oh, it gives you not density; it gives you this what they call C sub n.
Yes, that's right. Yes, I mean that's a good
source of C sub n, not of n
squared. Yes.
Okay.
Yeah.
Thank you, Roger.
Don't blame me. And the question I was going to ask for Jim, because I confess that I missed the first 5 minutes, I think, of your talk this morning. You may have covered this. The extreme scattering events, which are more challenging in terms of interpreting them in terms of interstellar physics. What do you now think about those?
I only mentioned them in passing as an example, so I didn't really talk about them, other than to say, it seems to be some kind of lensing sort of geometry. But I guess I would still fall back on the paper that you and Roger Romani and I wrote in 30 plus years ago. That there are sheets, and sometimes you see them face on and sometimes edge on. You do have an overpressure problem, and that's the big issue. Yeah. And then, Harish, I don't know if you want to talk about your 0.4 parsec thing.
Yeah, I could mention. It's not related to FRB, so I'll just be very quick.
Yeah, I want to bring
we'll
things
talk
back
later,
to
Roger.
FRBs.
It's not related to FRBs, yeah.
I want to ask about FRBs. My impression, Jim, was that when you talked about scattering, you didn't talk so much about scattering right next to the source. You talked about scattering and our galaxies, scattering and host galaxies.
Right.
Not so much about in IGM and not so much about the source. Do you have any ideas about that?
Well, yeah. I mean, for one thing, I would say that we know that scattering happens in the Milky Way. So I was sort of going down the list of things that we know happen or are likely to happen. So the host galaxy scattering for sure. I mean, as you know, there's a geometric deleveraging of anything, the closer it is to the source, the more CN squared you need to have, and that type of thing, or more column density. So if you can arrange that and avoid free absorption, then sure. Now,
is something like this required to explain observations, for example?
I'd say not yet.
Not yet.
I mean, if we saw I think the changing RM in 121102 is a very good argument for why it's close in, whether the Faraday medium's relatively close in. If we saw a rapid change in the scattering, the scattering tail of some repeating FRB, you'd make the same argument, and then you'd have to have something close in.
Okay, but nothing like this has...
Not that I don't believe so.
So from your talk, if you have a scattered Brownian extragalactic source that's like a milliarc not going to scintillate in the galaxy because it's not significantly smaller than a microarc.
Right.
What if you have a 10 microarc second source? Presumably this is a continuous
Yeah.
thing.
Yeah.
What happens to the autocorrelation function, I guess?
Well, do you mean what happens to the intensity fluctuations?
Yeah, I mean, like how quickly do you quench that galactic
Yeah.
scintillation as a function of the angular size?
Yeah, it goes something like it's linear. It's theta critical over theta. So
do you believe the sort of upper limit that's placed on the scattering screen for that GBT Misui burst?
yeah, I think that's reasonable. Yeah, they place it within 40 kiloparsecs of the source and of the galaxy. And so it's likely to be in the galaxy. I think that's still the most stringent limit. But it's a game that could be played for any FRB if you see galactic scintillation.
Yeah, that's right. Especially if you go to lower galactic latitudes.
Right.
You still see scattering.
Yeah.
Say something about where the screen is in the host galaxy.
Well, the 121102 shows galactic scintillation, and it's for I think it's very lucky, right? Because it's towards the anti-center, even though it's right smack in the galactic plane. So it's fine scale structure. But we don't see any host galaxy scattering. Isn't that right, Laura? We still don't see any scattering tail. So you can't really constrain the location. I mean, there's an upper bound on the scattering, so you can use that, but it's not it's like a megaparsec is the limit.
Laura?
Pointed in my direction. I have a sort of related question, which is, let's just hypothesize for the moment that the scattering that we observe does come from the host and not, CGM or IGM.
Yeah.
You have a sense of whether it's primarily dominated by the line of sight through the ISM in the host, or is it primarily dominated by some small-scale structure, either close to the source or that happens to be along, in other words, is a small-scale structure dominating the scattering, or is it the actual integrated ISM throughout the host? And is there any way to distinguish those two?
Yeah, it's the same question you can ask for any galactic pulsar.
Yeah,
too, right?
If you know that answer, I'd be curious as well.
Well, we see changes in scattering of the Crab pulsar, fairly dramatic, but that's because you've got all these filaments and things that are, as far as I know, there's no example of a galactic pulsar where you see changes you don't see changes in the pulse broadening. We see all kinds of wild stuff in the dynamic spectrum. But that's sort of that's explainable, but not by having any special thing along the line of sight, typically. So how would you tell? I think it would have to be time variability, unless you had an optical. If it was a nearby FRB and you could resolve regions in the galaxy, that might be a good case.
Right.
For host galaxy scintillation from 121102?
More or less. I mean, as you know, we wouldn't know the frequency scale offhand, and so there's confusion with all the trombone structure and the spectral islands. So in a sense, we've looked, but I would say nothing pops out that would force you to say that it's host galaxy scintillation.
Jason?
See, there's something different. Is that okay? Yeah, it's related to this.
Wait a second. Oh, okay.
Well, I was just going to say, so you showed the echoes for the Crab pulsar,
Right.
and there's a couple slow vanilla pulsars that show such echoes at LOFAR frequencies. That might be something that we should be looking for in FRBs as well, like echoes of the pulse.
Maybe Ryan has seen them.
Well, I mean, they should have you should be able to see them as, I guess, very steep spectrum
You mean
components.
so chromatic?
Yeah, there should be strong chromaticity to the.
So how do we tell that they are echoes and not, other pulses? Is there a distinguishing characteristic we should be looking for?
Chromaticity.
Yeah, I think if
correlated voltages.
Okay.
Yeah.
Yeah, that as well.
Andre, you had a point?
Is it okay if I slightly change the subject, or should I wait?
No, change.
I wanted to ask you, this thing, so So you showed all these many rotation measures for various sources, and all of them are way below this FRB, which we talk so much about, 121102. We also had some discussion about how much of the rotation measure can be intrinsic to the host galaxy or to our galaxy. So do I understand correctly that with the exception of FRB 12 whatever, all others are consistent with having virtually zero intrinsic rotation measure? Is it a possible interpretation? Do I understand this exchange correctly?
No, a lot of them do. Most of them, in fact, have RMs that are originating in the source and the progenitor.
How do you know?
Well, we're basically sort of subtracting the galactic foreground from
No, but I mean the
data.
host galaxy. Can it all be due to the host galaxy of FRBs, or should it be circumburst?
Oh yeah, that we don't know. We're basically ascribing everything to the host galaxy and the source itself, but I think you need.
But could this source itself have virtually zero rotation measure?
Potentially,
because
I guess.
Look, we are like theorists. We are operating. Oh, there is this rotation measure 10 to 5 with lots of constraints.
No,
maybe this is one. So
I guess, right?
So the answer is yes. It can be zero.
Potentially, yes, because if you look at the chime, if you're saying all repeaters are sort of the same sources, and then you're saying it's from the nebula could have dissipated, right? And in that case, you'd get negligible RM from the nebula, and a lot of it maybe you have H2 regions or something along the line of sight. So.
Liam, you have a comment?
Yeah, I think just to flesh that out and to agree with Sterl's point from before, if you have an RM of 500, it's probably in an atypical place in the ISM of the host galaxy, but there's no reason to think that RM is coming from within 10 to the 13 centimeters. You know.
Or even 10 to the 17.
Yeah. Or even 10, yeah.
I guess so to answer your question, I think the way to test this is for the chime repeaters to see if there's any time variability in RM. Right? I think that's the way we have.
But theoretically, it is okay to entertain the possibility that rotation measure can be as small as 10 or smaller.
Yeah. Laura, you have a.
Theoretically, it depends on your model.
No, but I mean from the data itself, it's not forced upon us.
That was what was unclear to me, and I'm glad Sterl helped clarify that.
Laura, you have something?
I just want to make a very brief comment, which maybe Manisha made for sort of the theory people in the audience. I think very generally, the FRB surveys that we have done up till now would have very hard time finding any rotation measure above about 10,000. The reason we could do it from the repeater is because we could go back and observe at higher frequencies. And I think even talking to the chime people, at the moment, they would have, given their current analyses, have a difficulty identifying rotation measures above on the order of 10,000 or maybe, up to maybe 1,000 or so. They can do it eventually, but at the moment, it's tricky.
You're saying when we did not measure rotation measure, it could be 10 to 5.
I'm saying, yes, when we have not measured, it could be 10 to 5. And we have many bursts for which we have never measured rotation measure because we simply don't have the polarization capabilities.
So my question. So if you measure rotation measure, that's the actual rotation, and not like it could be higher. So
it's an actual measure.
And if in this case of it being so high not to measure it, that would depolarize the burst, and it would be unpolarized.
Yeah, like Emily's FRB, which has roughly 0% linear polarization, could have an RM of 10 to the 5.
So my question is, what fraction of FRBs are unpolarized by this definition?
Not huge. Surprisingly small. One or two of a dozen, maybe?
Yeah.
2 or 3 of a dozen?
But not many.
Okay, but that's it. If we think almost all these mechanisms should produce some polarization, that's interesting information.
You do measure some rotation measures for some of them, right?
Yeah.
And they are at the hundreds.
No. We've
but the point is, observation is very difficult to measure 10,000. So that this jump is could be artificial.
Yes, but
is what I'm saying.
But you do measure some. You measure some with hundreds.
Yeah.
So what you would be saying, okay, there's a group at hundreds and there's a group of 10 to the 5. Because 1,000 you could still measure. No. And you don't see them. No, to be completely clear, there are many that we can measure low rotation measures, and there are a few that either
they are unpolarized or the rotation measure is very high and we don't know.
But if there is this population of very high, there would be sort of two groups. One which has this 100 sort of RMs and one which has this 10,000 and you not.
Yeah,
and the 1,000 RM are missing.
Once you approach the cutoff of your telescope, the cutoff in RM is pretty steep.
Right, but then I would expect to see a range and the cutoff at the technical limit.
Yeah, no, I
but
understand.
This is not what we see. We see a lot well below and nothing between this and the limit, and then maybe there's something.
At CHIME, I don't know about ASCAP, but CHIME we still don't have this full analysis.
Yeah.
So
right,
we're still working.
I think the data that we have now is sort of this.
Yeah, like the ASCAP bursts, sort of what, you know, we've measured detected polarization for all of them, and we've measured rotation measures for all of them that we've can measure rotation measures for. And the maximum is 380, but most of them are 10, 20.
Yeah. Right. So you have this group of very low, and then it could be that you have this very low rotation measure group and very high rotation measure, nothing in the middle. But I think this is sort of
maybe in the middle,
invention.
which is Manisha's burst, which has a very high DM. No, but the one that you have, which is a couple hundred, but in the rest frame, if the redshift really were the DM, it would be a couple thousand.
Yeah, it's a bit surprising that we don't have like 2,000 or 3,000 measured. I think.
That was the general point with these nebular models, is that the RM in our fiducial model is dropping as t to the minus almost 4. And so if you have a source that's twice the size, its rotation measures, its orders of magnitude, very quickly dropping. So if you sort of sampling at the different phases, you're going to see some when it's just ejected, just becoming transparent, and RM is enormous, and then very quickly it will become insignificant compared to whatever background you have.
Yeah,
sorry, if RM is t to the minus 4, your chances of getting 10 to the 5 are hopeless compared to getting 10, right? That doesn't work.
Well, but it could be more actively bursting.
Yeah, I have to fold in activity, but yeah.
You say it's also more active anyways.
In wire wave bursts with just RM of 10, it should be impossible to find them. They're so less active. I guess one has to do the statistics.
So yeah, I think I mentioned this briefly in my talk, but the very naive calculation of if you fold in the activity that goes as some energy injection power law and take the RM that's predicted from that same energy injection power law, then you'd expect for moderate energy injection power laws, you'd expect sort of a power law, a logarithmic distribution of rotation measures. So basically you'd have about equal chance of finding RM of 10,000 as 10. But yeah, we are missing the 1,000 ones, I agree.
Any other points that people have about effects of propagation? We have exactly 2 minutes.
I just want to, maybe I can ask Xavier. For me, one of the interesting things in scattering is the circumgalactic medium, because there's no other way to do it other than having FRBs. And so I just wanted to ask for the ASCAP folks, is that reasonable to isolate CGM scattering? Are you close to doing that?
Is too strong a word. As you know, you get the integral right of the entire sightline, and so you can make statistical arguments, particularly once you have some confidence in what the host is doing, if you can. But yes, it'll be a statistical approach where you can isolate. How many halos are in front of this sightline or that sightline, and enable you to make inferences about the magnetic field.
Wenbin?
Oh, can I ask a question? So when people make this plot DM versus scattering time at 1 gigahertz, can you just make it for the ones we have host galaxy, just subtract the IGM DM, because that's not relevant in the x-axis. Just move it so that it's subtract the Milky Way, of course, and then just look at the kind of the host. If we kind of have, there are limits on the host, so you put error bars and see if they are consistent with the Milky Way. I mean, you put some error bars. You put some limits, so that it goes to a lower DM side. So you put that.
The problem is you don't have redshifts.
I mean, the ones with identified hosts.
Agreed.
Yes.
Okay, on this note, I think we are out of time. And I think I want to thank all the panel members and all the speakers for this session and continue discussion at lunch.